Here we start the module, the stellar evolution. First of all, we discuss the topic, the birth of a star. So, a star can be thought as it is born when the core temperature of the protostar reaches about 10 million Kelvin. So, a protostar is defined as the seed from which a star is born. It's actually a cloud of gases and dust, but it may resemble a star, but it is not really a star because no nuclear reaction occur in the core of the protostar. So it is a gravitationally collapsed dust and interstellar medium. So it's not considered as a star. So a star is considered to be born when the temperature of the protostar increases up to 10 million Kelvin. So at this temperature, the hydrogen fusion can occur by the process of proton-proton chain. So we will discuss this proton-proton chain in detail in the next session. So when the fusion process starts, the further gravitation collapse of the protostar is stopped. So the star's interior structure stabilizes. So thermal energy created by the nuclear fusion maintain a balance between the gravity and pressure. So this process is known as gravitational equilibrium. So this is also called hydrostatic equilibrium. So now, till now, the star is not, the protostar is not considered as a star. So when the fusion starts, it is considered as a star. So now the star is a hydrogen burning main sequence star. So we know that all the main sequence stars are hydrogen burning. That means hydrogen fusion occurs in the main sequence stars. Okay. So now the time taken for the formation of a protostar to the birth of a main sequence star depends on the star's mass. So that means the star's mass plays an important role. So you have to remember that the massive stars do everything faster. For example, a high mass protostar may collapse in only a few million years or less. But a star with a mass of 1 solar mass, 1 m theta is the solar mass, could take around 50 million years for from the stage protostar to the star. A star with a very small mass, for example, an M-type star, could take 100 million years to collapse. So massive stars will take only a less time from the stage protostar to a star, a million year or less. But very small mass stars take 100 million years to collapse. So a very massive stars in the young cluster may be born, live and die before the smallest star finish their infant stage. ഒരു ക്ലസ്റ്ററിൽ തന്നെ മാസീവ് ആയിട്ടുള്ള സ്റ്റാർ ഉണ്ടാവാം, അതുപോലെ തന്നെ മാസ് കുറഞ്ഞ ലൈറ്റ് സ്റ്റാർസ് ഉണ്ടാവാം. ഈ മാസീവ് സ്റ്റാർസ് പെട്ടെന്ന് തന്നെ എല്ലാം അതിന്റെ പ്രോട്ടോസ്റ്റാർ സ്റ്റാർ സ്റ്റേജ് എല്ലാം കഴിയും. അപ്പൊ ലൈഫ് ടൈം കംപ്ലീറ്റ് ചെയ്യും. സോ ദേ മേ ബി ബോൺ, live and die before the smallest star in the cluster finish the infant stage. അപ്പോൾ smallest stars അതിന്റെ infant stage protostarൽ നിന്ന് സ്റ്റാറിലേക്ക് എത്തുന്ന സ്റ്റേജിലൊക്കെ ഹെവിയർ സ്റ്റാർസിന്റെ ലൈഫ് ടൈം കംപ്ലീറ്റ് ആയിട്ടുണ്ടാവും. ഓക്കെ. So the changes that occur to a protostar's luminosity and surface temperature can be shown on a special HR diagram. So this HR diagram is known as the evolutionary track or life track of a star. So the transitions that occur to a protostar's luminosity and surface temperature can be shown on a special HR diagram. So, നമ്മൾ ഇതുവരെ കണ്ട HR diagram different stars in the temperature and luminosity and represented. ഇവിടെ ഒരു സ്റ്റാറിന്റെ തന്നെ stages, protostar to main sequence star ഉള്ള transitions അപ്പോഴുള്ള അതിന്റെ luminosity-ലും surface temperature-ലുള്ള changes കാണിച്ചിട്ടുണ്ട്. So such a diagram is called the evolutionary track or life track of the star. So each point along the star's track represent its luminosity and temperature at some point during its life. So, and this evolutionary track shows us how the protostar's appearance changes due to the changes in the interior. So now the figure shows the evolutionary track for several protostars of different masses. From 0.5 times the mass of Sun to 15 times the mass of Sun. So these are all represented in a single diagram. So this represents the evolutionary track of a star having mass 0.05 times the mass of the Sun. So the arrow is along this direction. Okay, so this starts from here and finally ends in the main sequence. The protostar stage, the luminosity is somewhat higher and the temperature is somewhat lower. Current temperature lower ആണ്, temperature high ആവുമ്പോഴാണ് the main sequence ആയിട്ട് മാറുന്നത്. So different masses ഉള്ള stars ന്റെ evolutionary sequence life track കാണിച്ചിട്ടുണ്ട്. 1 m theta, m sun, 2 times the mass of Sun, 3 times mass of Sun, 5 times and up to 15. അപ്പോൾ ഓരോന്നിന്റെയും life track different ആണ്. Okay. So this shows the pre-main sequence life tracks. This evolutionary tracks are theoretical models and can be shown that they are in agreement with the experiment also. And we know that the protostars are relatively cool. Their temperature is smaller than the actual star. So the tracks all begin at the right side of the HR diagram. So നമുക്കറിയാം HR diagram surface temperature right നിന്ന് ലെഫ്റ്റിലേക്കാണ് increase ചെയ്യുന്നത്. So the protostars are all at low temperature. So they are at the right side of the HR diagram. And also the evolution, subsequent evolution is different for stars having different mass. So from this evolutionary track, you can see that this evolution is different for stars having different mass. എല്ലാത്തിന്റെയും path ഒരുപോലെയല്ല, they are different. Okay. So now in the figure, the evolutionary life tracks of 7 protostars are shown. These are the stages reached after an indicated number of years. So this dashed lines represent the years. So it take 10 to the power 7 years to reach the stage, and it take 10 to the power 6 years to reach the stage, and like that. And the mass shown on each protostar, 0.5 m Sun, 1 m Sun, etc., are the final mass when it becomes a main sequence star. Initial mass alla, finally adoru main sequence star ആവുമ്പോഴുള്ള mass ആണ് ഇത് കാണിച്ചിട്ടുള്ളത്. And greater the mass, the higher the temperature and luminosity. So 1 times the mass of Sun ആകുമ്പോൾ ടെമ്പറേച്ചറും കൂടുതലാണ്, luminosity കൂടുതലാണ്. എല്ലാ ലൈഫ് ട്രാക്കിലും നിങ്ങൾക്ക് കാണാൻ പറ്റും luminosity കൂടുതലാണ്, ടെമ്പറേച്ചറും കൂടുതലാണ്. Okay. So now as an example, we look at the evolutionary life track of a protostar. That is the star having a mass having 1 times the mass of Sun. For example, sun in the evolutionary track. So, the period in the star's life has 4 distinct phases. So, we will discuss those phases in detail. The phase 1 is that the protostars forms from a cloud of cold gas. And since the temperature is very small, it is on the right side of the HR diagram. But its surface area is enormous and therefore the luminosity is very large. So it may be 100 times more luminous when it becomes a star. So from this figure, it's clear that the luminosity is high and the temperature is small. Now the phase 2 is that due to its large luminosity, the younger protostar rapidly loses the energy it generated through gravitational collapse. And the further collapse proceeds at a relatively rapid rate. So there is a gravitational collapse, so the luminosity decreases. And its surface temperature increases slightly during next several million years. But the diminishing size reduces the luminosity. So the evolutionary track, the progress in this figure, it is clear to you. The temperature increases and the luminosity decreases almost vertically. Now the phase 3. So here the core temperature has reached 10 million Kelvin. So the hydrogen fusion starts. Hydrogen nuclei fuse into helium. So the rate of nuclear fusion is not sufficient to halt the gravitational collapse of the star. But the gravitational collapses slow down. So as the star shrinks, the surface temperature increases. And the process of shrinking and heating will result a small increase in luminosity. Temperature increasing, luminosity increasing. So over the next 10 million years. So the evolutionary track now progress leftward and slightly upward on the HR diagram. So HR diagram this region, we sun in the case discuss vertically decrease and slightly increases. Luminosity and temperature increases. Okay, towards left. In the fourth phase, both the rate of nuclear fusion and the core temperature increase over the next tens of millions of years. So once the rate of fusion is high enough, the gravitational equilibrium is achieved. The gravitational collapse halt and the fusion become self-sustaining. So the result is that the star settles onto the hydrogen burning main sequence. So this stage the main sequence part of star birth start the protostar and star consider. So main sequence star object star consider. The figure represents the evolutionary track of a protostar. So this is the interstellar cloud. This is phase 1. There is no radiation escape from the interior of the cloud. We will discuss it. And in the phase 2, the protostar shrinks and heat up. And in the phase 3, the shrinking slows down and the temperature increases. And in the phase 4, the fusion rate increases and the point is reached where the gravitational equilibrium is achieved. And it is a part of main sequence. ഓരോ ഫേസസും മാർക്ക് ചെയ്തിട്ടുണ്ട്. phase 1 ഇവിടെയാണ്, phase 2 ഏകദേശം ഇവിടെയാണ് വരുന്നത്. Then phase 3, phase 4 on the main sequence. പക്ഷേ ഒരു ഒബ്സർവർക്ക് ഈ എവല്യൂഷൻ ഡിറ്റക്റ്റ് ആയിട്ട് കാണാൻ പറ്റില്ല. Even though the luminosity of the protostar stage is very high, we cannot see this. That they are surrounded with vast clouds of interstellar dust. So they are very efficient at blocking out light. So they will not pass light, so we cannot observe. So the dust in the vicinity of the protostar are often called the Coco Nebula. So this Coco Nebula absorb light. So it is very difficult to observe the evolution stage at visible wavelengths. But using infrared wavelengths or infrared spectrometers, we can observe them. So, നേരിട്ട് observe ചെയ്യാൻ പറ്റില്ല, infrared spectrometers വെച്ച് observe ചെയ്യാം. Okay.